Wet bulb temperature. The wet bulb temperature is the temperature at which air may be cooled by evaporating liquid water into it isobarically, that is, at constant pressure until it is saturated. The air parcel uses its own internal energy to evaporate the liquid water, so U decreases over time and hence T decreases as well. But because we're driving evaporation, the amount of water vapour is increasing, so R increases, and therefore TD increases as well. So the temperature and the dew point temperature converge on this value known as the wet bulb temperature. All the sensible heat removed from the air parcel is stored as latent heat. So no heat is lost from the parcel, neither enters nor leaves, and hence this process is a moist adiabatic one. There are two versions of the process shown on the diagram. The blue and the red arrows indicate the actual process. The parcel's temperature decreases from T to TW because sensible heat is being removed from the parcel. Its internal energy is decreasing. The dew point temperature approaches the wet bulb temperature because the amount of water vapour is increasing over time via evaporation. So there's a DR, the mixing ratio increases. We can also do this in a pseudo-adiabatic sense using the green lines. So, lift the parcel along a dry adiabat and an isoplatha mixing ratio until the two lines intersect. That is, we have condensation. The parcel reaches its lifting condensation level. Now lower the parcel along a saturated adiabat back to the original pressure and we attain the value of wet bulb temperature. That's also shown here in this schematic. Parcel's lifted from its original pressure level along a dry adiabatic lapse rate and from its original dew point temperature along a line of constant mixing ratio until they cross at the lifting condensation level. Ignore during this process the heat capacity of liquid water and ice. Descend along the saturated adiabat to the original pressure and we get the pseudo wet bulb temperature. The moisture added here is the mixing ratio at the pseudo wet bulb temperature minus the mixing ratio of the original dew point temperature. Finally, we can take the parcel and lower it to 1000 hectopascals and get the wet bulb potential temperature, or to be precise, the pseudo wet bulb potential temperature, which is actually conserved for saturated adiabatic motion. So it's another conserved quantity and it's a useful label for saturated parcels. Finally, the concept of the wet bulb temperature is useful in thinking about the formation of cloud during rainfall. Consider a cloud precipitating into an unsaturated level. Some of that liquid water will evaporate and it will cool the layer and increase the dew point, or the mixing ratio. Should that layer eventually become saturated, you will get the formation of stratus. This is particularly important for aviation forecasting, where if you get stratus below a certain base of 5 or more octaves of cloud so that more than half the sky is covered, aircraft flying under visual flight rules, that is rules where they need to see the surface of the Earth, will be required at an aerodrome to have sufficient fuel to circle about until this cloud clears or find an alternate. This process is also of importance in the formation of something known as nimbostratus, which is mid-level cloud that's particularly deep, so the base of the cloud continually lowers due to this wet bulb process.